Welcome to this deep dive. Today marks the official start of something really crucial, our in-depth exploration of cooperative AI concepts. Consider this, Cooperative AI Notes, Episode 4, and, well, the beginning of our formal teaching in this vital area.
Exactly. And for you listening, if you're focused on understanding how we can really architect the next generation of safe and beneficial AI,
Right.
especially when we're talking about multiple AI agents interacting or AI working closely with humans, this is really where we begin to lay that groundwork. We're going, right to the heart of cooperative AI.
Okay, so let's unpack cooperative AI then.
Yep.
At its core, it's a field dedicated to understanding and enabling cooperation.
Yeah.
And that's cooperation in a couple of key ways.
Yeah.
First, how can we design artificial intelligence agents so that they can effectively cooperate with each other? And second, how can these, increasingly intelligent systems truly cooperate with us?
And what's fascinating here is that while we've seen just incredible progress in AI and machine learning, a lot of the historical emphasis maybe has been on AI excelling in competitive scenarios. Think about mastering games like Go, chess, or even really complex strategy games.
Yeah, the big headline grabbers often.
Right. Cooperative AI deliberately shifts that focus. It asks us this really fundamental question. How do we build AI from the ground up with the primary goal of working together for mutual benefit?
Right. And cooperative AI isn't like a completely new invention, is it? It builds upon a pretty rich history of research.
Oh, absolutely.
We're talking about multi-agent systems, which have long studied how independent agents interact. Then you've got game theory and social choice theory.
Crucial frameworks.
Giving us these powerful ways of understanding strategic decision-making and how collective preferences kind of emerge. And crucially, human-machine interaction and the whole field of AI alignment are vital for making sure that AI cooperation actually lines up with human values and goals.
Yeah, can't forget those.
And, natural language processing too, which is just essential for communication between agents and between AI and humans, plus things like social tools that can help build collaborative AI environments.
But it's really important to understand that cooperative AI isn't just like a collection of these existing fields thrown together.
Okay.
As our sources really emphasize, it's a concerted effort to develop a unified theory and a shared vocabulary specifically focused on the principles of cooperation within AI.
So like a common language for it.
Exactly. It's about creating that common language and set of concepts to really facilitate focused research and build bridges across these related areas, all with the aim of understanding and actually fostering cooperation.
Okay. So we're starting to get a picture of what cooperative AI is.
Yeah.
But what are the big unanswered questions? What are the fundamental hurdles we need to clear as this field moves forward?
Yeah, let's dive into that.
Let's get into some of the key open problems and challenges.
Okay, so one of the most significant challenges, and this comes up across our sources, is just the inherent difficulty for AI agents to accurately model and predict the behavior of other agents.
Right, understanding the other guy.
Exactly. To truly get outcomes that benefit everyone involved, an AI needs to go beyond just understanding its own goals. It really needs to grasp the beliefs, the intentions, and the likely actions of those it's interacting with.
The Cooperative AI Study Guide uses the one-sided assurance game as a perfect illustration of this, doesn't it?
It does.
If one AI agent isn't confident that another one will cooperate, it might just hang back, be hesitant to cooperate itself. Even if mutual cooperation would actually lead to the best possible outcome for both of them. It's a real challenge in building that trust and shared understanding.
Precisely. Then we face the really complex task of designing the underlying structure of these multi-agent systems that sort of distributed institutions and norms.
The rules of the road, kind of.
Yeah, exactly. The rules that can guide individual AI agents towards behaviors that benefit the entire system. Think about like the unspoken rules of a really well-functioning team, or maybe the traffic laws that keep our roads, relatively safe. How do we create AI equivalents?
Right, equivalents that can promote cooperation on a huge scale and in all sorts of different situations.
Yeah.
It sounds like we're not starting completely from scratch there, though. I think our sources mentioned existing foundations. Things like languages for formally expressing societal objectives.
That's right.
And even model checking, which essentially allows us to mathematically check if our AI systems, given their rules, can actually achieve the cooperative outcomes we want, like testing a blueprint.
Absolutely. The foundational work is definitely underway. But the challenge really ramps up when we think about systems that involve both humans and AI agents working together.
Ah, the mixed teams.
Yeah. How do these mixed systems develop and enforce social norms? And crucially, how can AI learn and generalize these norms? Meaning, how can an AI understand the nuances of human cooperation and then apply those lessons effectively in new situations and when interacting with different partners, whether they're human or other AIs?
Okay, here's where it gets really interesting for me. Because as AI gets better and better at cooperating, are there potential downsides? Things we need to watch out for. It's not all going to be positive, is it?
That's a critical point to consider, definitely. Our sources raise several potential pitfalls. One really significant concern is the risk of harm to those who are, maybe, excluded from a highly cooperative group.
Excluded. How so?
Well, if one set of AI agents becomes exceptionally good at working together, could that inadvertently disadvantage or maybe even harm individuals or groups outside that cooperative circle?
I see. Yeah, any kind of exclusive cooperation could create an us versus them dynamic. That makes a lot of sense. What other challenges should we be thinking about?
Another important one is the potential for highly effective cooperation to actually undermine pro-social competition.
Undermine competition. But isn't competition good sometimes?
Well, healthy competition can be a really powerful driver of innovation and improvement, right? But if cooperation becomes too dominant or maybe too tightly knit, could it morph into something like collusion?
Like price fixing, but with AIs.
Potentially, yeah. Stifling progress, leading to negative outcomes like market manipulation or suppressing beneficial alternatives. The study guide also touches on the, well, unsettling possibility that advancements in cooperative skills could also enhance harmful coercive capabilities.
Coercive, like deception.
Exactly, like deception. If AI gets better at understanding and working with others, could those very same skills be turned towards malicious ends?
Yeah, that's a sobering thought. It really highlights how cooperation and concepts we might think of as opposites, like coercion and competition, might actually be, more deeply linked than we first think.
Exactly. Successful cooperation in human societies often relies on things like pro-social punishment. Think of just social disapproval or even legal sanctions for people who break cooperative agreements.
Right, keeping people in line.
And as we've touched on, competition itself can sometimes be a catalyst for cooperation. So disentangling these elements and understanding their complex interplay within AI systems, that's a really significant challenge for the field.
Now, okay, the dynamics of cooperation between AI agents, they aren't necessarily going to just mirror how humans cooperate, are they? Our sources point to some potentially pretty significant differences in machine-to-machine cooperation.
Oh, definitely. What's fascinating here is the potential for AI to cooperate in ways that might be completely novel, even alien to us.
Like how?
Imagine AI agents communicating with each other at incredibly high speeds, showing strategic responsiveness far beyond what humans can manage.
Okay.
And perhaps even sticking more closely to purely rational decision making, at least, in theory.
But wait, there are potential downsides to that increased efficiency and rationality too, right? Didn't one paper mention the risk of AI developing hard-to-interpret emergent languages?
That's a key point, yes. That could make it incredibly difficult for us to understand their cooperative strategies or even just be sure they align with our goals.
So we wouldn't even know how they're cooperating.
Potentially. And AI systems can sometimes be very sensitive to specific scenarios. A cooperative solution that works perfectly in one sort of narrow set of conditions might completely fall apart if those conditions change just slightly.
Griddle cooperation.
Kind of. Furthermore, machine learning algorithms have this well-documented tendency to discover unexpected and sometimes pretty undesirable solutions.
The infamous reward hacking.
Exactly. This inherent unpredictability just adds another layer of complexity to the challenge of ensuring safe and reliable AI cooperation. The potential for far greater strategic complexity in interactions between AI agents is just immense, and we need to be ready for cooperative behaviors that might not line up with our human intuition at all.
Wow. Okay, this paints a picture of a really intricate, multifaceted challenge. And it leads us straight to a crucial question. Even if we manage to align individual AI agents with our specific objectives, Does that automatically guarantee safety and good outcomes in a multi-agent setting?
And this is such a critical insight. The answer, according to, well, pretty much all our sources, is a resounding no.
No,
Yeah. Even if we have a group of individual AI agents that are all, let's say, perfectly aligned with their intended goals, the interactions within that multi-agent system can still lead to undesirable and even unsafe outcomes.
Okay, so good intentions at the individual level don't necessarily add up to good collective results. Why? Why is that?
The study guide talks about this concept of emergent functionality, particularly in groups of large language model agents, LLMs.
Emergent functionality.
Yeah, when you bring multiple LLM agents together, they can develop capabilities or show behaviors through their interactions that just weren't present in any of them individually.
It's like a sports team.
Yeah. The strategies and plays they develop together are more than just the sum of each player's individual skills.
That's a helpful way to think about it.
Yeah.
So even if each individual LLM is aligned, these emergent things could still lead to, well, problematic situations.
Exactly. Our sources specifically mention the risk of LLM agents engaging in collusion.
Collusion again.
Individually, an aligned LLM might not do something harmful, but a group of them, interacting and potentially coordinating their actions in ways we didn't foresee, they could find pathways to negative consequences that just wouldn't happen with those same agents working alone.
And it's not just about unexpected behaviors popping up, is it? I think one paper touched on how individual alignment doesn't necessarily preserve our desired welfare orderings when we try to add up the outcomes across multiple agents.
That's right. That's another layer. Even if each AI agent is successfully pursuing its defined objectives, those objectives might be defined with, say, different scales of value or different underlying ideas of fairness. So when you try to combine these individually good outcomes to assess the overall well-being of the system, the initial alignment of each agent just doesn't guarantee a collectively desirable or, fair result.
This really hammers home the importance of thinking about safety at the system level, not just focusing on aligning the individual parts. So how do we even start to analyze and understand these complex multi-agent interactions? It feels like we need some kind of framework.
And that is precisely where game theory becomes so incredibly relevant to AI systems.
Game theory.
Yeah, game theory gives us this rigorous mathematical framework for analyzing strategic interactions between multiple decision makers. It's really all about understanding how different agents, each with their own goals and potential strategies, might interact and what kinds of outcomes can arise from those interactions.
Now, when many people think of game theory, they probably immediately picture competitive scenarios, games with clear winners and losers. Just go.
Right, the classic examples.
But our sources point out that the real world and the broader landscape of strategic interactions isn't always a zero-sum game, is it?
That's such a crucial point to understand. While a significant amount of historical AI research has focused on pure conflict games, what game theorists call zero-sum games, where one agent's gain is directly another's loss. These perfectly adversarial situations are actually pretty rare in the larger context of strategic interactions and arguably in most real-world scenarios. Even in games that have elements of conflict, the possibility of, say, costly actions that transfer benefit can create areas of common interest.
That's an interesting twist. So even if there's some built-in competition, there might be ways to encourage cooperation by making it strategically smart to help others.
Exactly. And the Cooperative AI study guide brings up the classic example, the prisoner's dilemma.
Of course.
In this scenario, the individually rational choice for each player is actually to betray the other one.
Defect.
Even though mutual cooperation would lead to a better outcome for both of them, it just perfectly illustrates that fundamental tension between individual incentives and collective well-being.
It's a classic for a reason, right?
Right.
It shows how focusing only on what seems best for me right now can lead to a worse overall result for everyone, including me, in the long run.
Precisely. And to further equip us with the tools to understand these dynamics, our sources introduce several key game-theoretic concepts that have direct relevance to studying and developing cooperative AI.
Okay, let's hear about these essential game theory tools for our cooperative AI toolkit. Lay them on us.
All right. First, there's the collective action problem. This refers to situations where there's like a cost for an individual to contribute to some shared resource or goal.
Okay.
But everyone benefits if enough individuals chip in. Think of efforts to reduce carbon emissions, as the study guide illustrates. My individual reduction might seem tiny.
Insignificant, yeah.
But if a large enough group participates, the collective benefit of cleaner air is substantial.
Makes perfect sense. It's that challenge of getting individual effort lined up with a shared benefit even when my part feels small. What's next?
Then we have the utilitarian welfare function. This is basically a way of evaluating the overall well-being of a group of agents just by summing up their individual utilities or, levels of satisfaction.
Okay.
The underlying assumption here is that each agent's well-being is considered equally important when you calculate the overall welfare.
So it's a way of looking at the total good generated for the whole group without necessarily worrying too much about how that good is split up among individuals.
In essence, yes. Next up is the Nash equilibrium. This describes a stable state in a game where no single agent can unilaterally change their strategy and get a better outcome for themselves. Assuming everyone else keeps doing what they're doing, it's a point of balance or stability.
Okay, stable.
Importantly, though, as the study guide points out, the one-shot prisoner's dilemma has a Nash equilibrium where both players defect, which is definitely not the cooperative outcome we'd ideally want.
Right, so a Nash equilibrium isn't necessarily the best outcome for the group overall, just a situation where nobody has a reason to change on their own.
Precisely. Following that is Pareto optimality. An outcome is Pareto optimal if it's impossible to make any one agent better off without simultaneously making at least one other agent worse off.
Okay, so it's about efficiency.
Exactly. It's a concept related to efficiency, making sure we're not in a situation where we could improve someone's outcome without hurting anyone else.
So Pareto optimality is about maximizing the total pie without waste, while Nash equilibrium is about individual stability. They don't always line up, do they?
Correct. They often don't. And finally, we have the common pool resource problem. This is essentially the flip side of the collective action problem.
How so?
It describes situations where a shared resource, like a public fishery, can get overused and depleted because each individual has an incentive to just take as much as they can for themselves.
Tragedy of the commons.
Exactly, leading to the eventual ruin of the resource for everyone.
Wow. These game theory concepts really give us a valuable way to frame why cooperation, even in AI systems, can be so tricky. But our sources also suggest we're not completely stuck, right? Institutions can play a big role here.
Absolutely. Our sources really emphasize how institutions, whether they're formal rules, informal norms, or even the carefully designed architectures of the AI systems themselves, can fundamentally change the strategic game being played.
Change the game.
Yeah, they can influence which equilibrium outcomes are most likely to happen. They can link different interactions together over time, or even directly change the payoffs for specific actions.
Like adding fines or rewards.
Exactly. The classic example of the repeated prisoner's dilemma, where cooperation can actually be sustained through strategies like tit for tat.
I scratch your back if you scratch mine.
Right. That shows how repeated interaction and just anticipating future consequences can foster cooperative behavior.
So by setting up the right rules and expectations, we can essentially kind of nudge agents towards cooperating more. One paper also mentioned that effective institutions often work by promoting better understanding between agents, enabling better communication, and letting agents make credible commitments to cooperate.
Exactly. Anything that helps agents better understand each other's intentions, communicate their own intentions clearly, and reliably commit to cooperative strategies. All of that can significantly strengthen the foundations for cooperation within a multi-agent system.
This is all incredibly insightful from a theoretical standpoint. But what are the concrete efforts happening now in cooperative AI to actually tackle these challenges and build more cooperative systems? What's happening on the ground?
Well, one particularly promising area of research is something called adaptive mechanism design.
Adaptive mechanism design.
Okay, the central idea here is to introduce a kind of planning agent into a multi-agent system.
A planning agent.
Yeah. This planning agent learns how to provide additional rewards, or maybe even punishments, to the other learning agents in the system. The goal is specifically to incentivize those agents to adopt and stick with cooperative learning behaviors. This often happens within what's called a Markov game framework, which is just a mathematical way to model sequential decision-making when you have multiple agents.
It's kind of like having a system-level manager or maybe a referee that can give out bonuses for good teamwork.
In a way, yes. By strategically stepping in with these carefully calibrated incentives, the planning agent tries to guide the whole system towards a state of higher total social welfare, where the collective benefit is maximized. And one paper offers some really compelling findings here.
Ah, yes. They even had those figures that showed it visually, right? Like figure 1C, illustrating how this adaptive mechanism design can actually shift the basic dynamics of a game, potentially getting rid of the classic social dilemma by reducing the fear and greed that might push agents apart.
That's exactly right. And Figure 2A shows a clear increase in the probability of cooperation between the agents over time when you implement this adaptive mechanism design.
Cooperation goes up.
Yeah. Then Figure 2B shows the actual extra rewards the planning agent is giving out to encourage cooperation. And interestingly, in some kinds of games, the need for this active intervention by the planning agent might actually decrease over time as the other agents learn to cooperate effectively on their own.
So it's like providing training wheels, maybe, helping them learn, and then they can keep the cooperative behavior going by themselves. The paper also mentioned an agent figuring out how cooperative its partner is based on the rewards it gets over time.
Yes, using a measure they call the time-weighted average reward, GREAT.
Great.
Exactly. By keeping track of the rewards they've received over time, an agent can sort of develop an understanding of whether its partner is also leaning towards cooperation and then adjust its own strategy based on that.
Right.
This allows for much more nuanced and adaptive cooperation strategies than just simple fixed rules might permit.
It really sounds like multi-agent learning in these environments where you have both shared and conflicting interests is a profoundly complex challenge. It's clearly not just a technical problem of coding better algorithms.
Yeah, at all.
There seem to be really fundamental conceptual questions about what we even want to achieve in terms of collective behavior.
Precisely. As our sources highlight, it involves carefully navigating the strategic context of the interaction, understanding the interplay between common goals and conflicting ones, and considering the problem from both the perspective of individual agents trying to optimize their own outcomes and the perspective of a social planner aiming for the best possible outcome for the entire system. The idea of achieving convergence to a Pareto optimal outcome.
Right, the efficient outcome.
Where we reach an efficient solution that benefits everyone as much as possible without hurting anyone else, that's often seen as a key desirable goal in multi-agent learning research.
And it's not only about designing incentive mechanisms, is it? Our sources also pointed to ongoing research focused on the very design of distributed institutions.
Yes.
That can naturally encourage desirable global behaviors within these multi-agent systems.
Absolutely. There's active work being done to develop algorithms that can help us predict which kinds of norms and rules will actually be most effective in promoting cooperation in different contexts.
Predicting effective rules.
Yeah. And what's particularly exciting is that AI itself is increasingly being used as a tool to explore the huge space of possible distributed institutions, potentially helping us discover new and maybe more effective ways to govern complex multi-agent systems.
This has been a truly foundational deep dive into the world of cooperative AI. We've covered a really significant amount of ground today.
We really have.
From defining the field and outlining its core goals to exploring the major open challenges, understanding why individual AI alignment just isn't enough for multi-agent safety.
Crucial point.
Examining the critical relevance of game theory and highlighting some of the cutting-edge ongoing research efforts.
And this is really just scratching the surface. The field of cooperative AI is a rapidly evolving landscape, and there's so many specific open problems and fascinating research directions that we just haven't had time to get into in this initial discussion.
But don't worry, because this deep dive, as you said, has only scratched the surface.
Yeah.
In our future discussions, we'll definitely be taking a much closer look at some of these specific open problems and the exciting state-of-the-art research that's actively working to address them.
Yeah, and understanding and effectively tackling these fundamental questions within cooperative AI is just absolutely essential as we move towards building increasingly sophisticated and interconnected AI systems. It's crucial for ensuring that these systems are not only aligned with individual goals, but also operate in a way that is collectively safe and, beneficial for all of us.
Absolutely. And on that note, here's a final thought for you listening to consider. Reflect on the really intricate principles of cooperation that we see in human societies, the subtle cues, the often unspoken agreements, the various ways we enforce cooperative behavior. How might these principles translate or maybe need to be fundamentally reimagined for artificial intelligence systems that could operate at vastly different scales and speeds of interaction than anything we humans have ever experienced? It's a truly compelling question, and one that will undoubtedly shape the future of AI development. Thanks for joining us for this deep dive.